Hey, this is Jericho with Team Starbuck, along with Gustav, Tim Spencer, Allison Tonkin, and Shannon Syme. And today we're going to demonstrate the relationship between position, velocity, and acceleration with respect to time. Now, to demonstrate this, we're going to drop a watermelon from the third floor of Tyler Hall, as drawn here on the board. We're dropping from a known height of 29 feet. The watermelon will then accelerate towards the ground at negative 32.2 feet per second squared, which is the acceleration due to gravity. Will then hit the ground at time t. We're going to have two timers set up that will time the duration of the fall, and from there we'll be able to calculate the velocity. We have two timers set up just to eliminate human error, as well as create or give the most accurate velocity that we can.
Hello, I am Gustav from Team Starbuck, and our team is discussing the relationship between acceleration, velocity, and position. So starting off, position is modeled by S, and that's just like where you are. And then from position we have velocity, which velocity equals a change in position over some change in time. That is the average velocity. And then acceleration is a change in velocity over the same period of time. So that is how you get the average velocity, average acceleration, and position we'll talk about later. But if you want to be more precise in your measurements, if you let time get smaller and smaller and smaller, basically go to an infinitely small number, it becomes dt, which as this gets smaller, that will get smaller also. So the instantaneous velocity can be talked about as as a change in position over a change in time. So ds dt. So ds dt is basically the derivative of position with respect to time. And likewise, as time gets smaller and smaller, acceleration becomes a change in velocity with respect to time. So velocity is the derivative of position with respect to time. And acceleration is the derivative of velocity with respect to time. So what we learned is that you can go from position to velocity by taking the derivative of the velocity of the position equation. You can go from velocity to acceleration by taking the derivative of the velocity equation. Likewise, you can also go from acceleration back to velocity, or back to position, by taking integrals. All right, so like we discussed, you can go from position to velocity to acceleration by doing derivatives. You can also go from acceleration to velocity to position by doing integrals. And I'll show you that here. So like we said earlier, A is equal to the change in velocity over the change in time. So if you solve this equation for dv, move dt on the other side, you end up with this. And if you integrate from both sides, this side you'll integrate from your initial time to any specific time. So from t naught to t. And this side you'll integrate from an initial velocity to whatever velocity you're desiring. So from initial velocity to your final velocity, you'll end up with, this side will be v minus v naught equals a t minus t naught. So then from there, you can solve for velocity and get that your velocity is equal to v naught plus your acceleration times time minus your initial time, which is assumed to be 0 in our situation. So now that we have velocity, we can integrate this again to get our position vector, to get our position equation. So our velocity equals our initial velocity plus our acceleration times the time in which it's affected, which is also equal to the change in position over some time. So if we solve, if we just look at this equation and put all the time, like solve for ds, we'll end up with v dt equals ds. And once again, we integrate both sides. This side from our t naught, which is equal to 0, to t. And this side from some initial position to the final position, s naught to s, we will end up with Vt minus V naught equals S minus S naught, which if you solve for S and plug in this equation for V, you will end up with this grand old equation of position equals your initial position plus your initial velocity times time plus 1/2 of the acceleration times your time squared. And this is the equation that we will use to calculate our approximate time for our demonstration. So our final time, which is when the watermelon hits the ground, is 0. Our initial time that we measured, as JERICHO said, is 29 feet. It started at rest, so our initial velocity is 0, so we can just ignore that altogether. And then our acceleration is negative 32.2 feet per second squared. Let me just clear that up a little bit. And all that is times time squared. So, solving for time, we approximate our time to be 1.35 seconds. And then once we plug this number into our equation for velocity, which is velocity equals our initial velocity plus the acceleration times time, this one started off at 0. You know, this acceleration is a negative 32.2 feet per second squared. And then once we plug in the 1.35 seconds, we get our velocity will be 43.47 feet per second.
All right, 3, 2, 1, go. 3, 2, 1, go. Ready? 3, 2, 1, go.
I'm Tim, and I will be analyzing the data from our test. Right here we have the average of our measured times. We came out to 1.1 seconds. So if you take that average and plug it into our equation for velocity, you get 32.2 feet per second squared times 1.1 seconds equals 35.42 feet per second. And you can see how this compares to our calculated over there. So we're going to take the percent error to see how far off we were. For that, we'll take the calculated velocity minus the measured velocity and divide it all by the calculated velocity and multiply it by 100%, and we get 18.5% error, which that's most likely from human error in the timing process. Also, in this equation, we neglected air resistance, which does play a role. So all of these were factors that could have contributed to our error.
I'm Allison, and in our conclusion, our goal was to be able to visualize the concept of motion and demonstrate the relationship between position, velocity, and acceleration. So in order to visualize this, we decided to drop a watermelon from the 3rd story of Tyler West. We did get a pretty big error, so if we were to do this experiment again, we would want to have a more accurate way of timing the fall and to have more trials, as well as being able to measure the final velocity.